Here we go. Okay, let's try that again. Thank you. Okay, let's go over what to expect. Again, it's not going to be that much different than Dr. Nogales. So, my lectures are lectures. I don't use PowerPoint. I only use the whiteboard. So I want to engage with you. I think oftentimes if we use PowerPoint, it's way too much information. In this class was like drinking from the fire hose. I kid you not. By the end of this semester, you will feel like, oh my word, more reactions? Yep. Then we get to the fun ones, like the Michael addition reaction, the Robinson annulation, all these really bizarre ones, okay? It just keeps building. So don't get behind in here. You're going on flashcards early on, you're going on learning these reactions, because this, you built a foundation. You haven't learned maybe a dozen reactions up to this point. You've worked with alkenes and alkynes. You've worked with alkanes. You combusted alkanes. Ooh, that's really exciting, right? Converted it to carbon dioxide and water. You might have oxidized or hydrolyzed an alkene. You might have put HBr across an alkene. Again, you haven't had a lot of reactions. Probably your Diels-Alder is your coolest one so far. Your 4n+2 is pretty cool stuff, right? With the electron withdrawing group, electron donating group, and all that fun stuff, right? It's all frontier molecular orbital fluid, by the way, which is what you get when you take advanced organic chemistry, which I just got done teaching last semester. So chemistry majors might get to take that, which is super fun because it explains the Diels-Alder as to why that works. And I love that chapter, so that's such a fun one. I missed teaching that chapter. I try to engage with you, and so my lectures are really eyes on eyes, eyes on faces, okay? Eyes on faces, because I know what most of you look like. Hey, some of you are just still math. I'm still not a big fan of these things yet, so I'm working on it. With that said, one of the things a couple of you are going to hate me for, what I want to set the precedent right up front, no laptops. unless it's something that you're taking notes on. Okay? This is fine. If you're going to take notes, but I want to engage with you. Oftentimes with laptops, it's a distraction. Because trust me, we're going to be covering a lot of ground, and it's going to get really gory really quickly. All right? And so I want full interaction, full attention, because that's how I teach. I teach very interactive. I look at eyes. I like to ask specific people questions. Hey, what happens if I oxidize a primary alcohol? Right? What happens if I reduce a secondary or a ketone? Right? So I want to ask, because I want you to engage with me. I don't want to just stand up here with a pen and write on the board. Right? I really want to engage. And sometimes I think there's a distraction. I found in my nursing chem class last spring, I had 63 in there. And the students that typically had their laptops open overall did poorer than the ones that just sat there and engaged. And so that's why this semester is a trial run. I just told nursing chem that, and I had like 9 students going, oh man, they shut them. I'm like, trust me, it's going to be a better semester. Because it's also distracting to me when I see your eyes down and not up. So I appreciate that. So I will try to make lectures super engaging. I'll try to bring in my experience through development of advanced pain molecules, some of my photochemistry at Berkeley, some of my other just pet projects that I've done through the years. I really like to engage. If you remember back to GChem, that was a long time ago. Those of you having for GChem, I have 2 degrees. I have a biology degree, and I have a chemistry degree, and I have a PhD in organic chemistry. So I have a lot of biology background, which is why I think I fell in love with organic chemistry. So I will try to bring a lot of the medicine, a lot of the biochemistry into it, because most of your biology majors, if not pre-med majors, okay? I think I have 3 chemistry majors in here, so, or 4, maybe 4. So with that, 2, 3, and then Nick is gone, so yeah. So with that, when I draw a molecule up on the board, we're gonna begin to look at its chemistry. How is it that I take something, for example, and I'll just show you an example of what this would look like. Let's say I take a molecule, very popular molecule right now in our culture, a very important molecule in the hospital. My wife uses this all the time, but it's also one of those that gets constantly abused, and it's constantly in the news, and some of you have probably heard of this, and it is called fentanyl. Okay, so there's fentanyl. Fentanyl has some really unique properties to it, and that's one of the things we want to begin to explore. What are those properties? What are we going to do with fentanyl? Now, to this point, there's a lot with this molecule that you guys are kind of looking at going, well, crud, I don't know a whole lot about that molecule. You might look at it and go, okay, I do know stick structures, so that's cool. I'll tell you what, I get sick and tired of doing this for nursing camp. This is exciting. Right? Don't you just love this? That's cool. Instead of just doing that, right? So you already have gone into stick structures. So you've already know shorthand organic chemistry. So you see that up here. You know this is some type of a not cyclohexane, but it's a 6-membered ring, okay? We haven't talked about amines. We haven't talked about aromatics. We haven't talked about amides. So we have some work to do. We have some functionality to go through. So that's why this semester is a ton of functional groups. You know those functional groups in the front flap of your book? You've gone through like 4 of them, 5 of them, okay? And we have like 12 to go. So that's why this is a very bulky semester. All right? We get to see the chemistry of this. But here's the cool thing. Look at this. Look what you do know, right? If you remember, the periodic table is like a window. It's a window through which I see something, and you're now beginning to see our window got really narrow, right? In general chemistry, our window was pretty big, was the whole thing, right? We talked about the lanthanides and the actinides a little bit. We did a little bit of nuclear chemistry down here with polonium and uranium. We talked about the transition metals quite a bit and what their charges were. We talked about the alkali earth metals and alkali metals. We talked about the non-metals and how non-metals like electrons. We talked about a lot of that. So our window was large. But what happened last semester is it got real small. It literally went down to 1 atom. It literally went carbon. So now we have to do what? Now we have to say, okay, what happens when carbon bonds with carbon? Well, there's 3 different ways it does it. Actually a 4th one that we haven't talked about, that's called aromaticity, which we will get to. Alkanes, alkenes, alkynes, right? You might have remembered the pKa of an alkyne being around 26. That's important. All right, we'll see that when we get back into organic metallics. You talked about alkenes. Okay, this is where your Diels-Alder came from. All right, there's your 4n plus 2, alkenes. So when your Diels-Alder did that, which is super fun, typically there's an electron withdrawing group here. Okay, oftentimes electron donating group here. Not always, you don't have to have it, you have to at least have this. You have to, but it speeds it up. We talked about alkenes. We talked about alkenes with hydration, right? We added water, probably with an acid, probably with a little bit of heat. And what did we do? Well, we formed a new functional group called the alcohol. We took the alkene and we hit it with a metal, and we made the hydrohalide, right? Kind of cool. Did we not do that yet? No? Doesn't look familiar? I think you guys talked, I'll go back and make sure, but alkenes were one of the functional groups. And I hope you guys talked about the alkyne. Did you not? I think you did. Okay. But again, we got a lot of functionality to go. Because on something like a fentanyl, we have other functional groups that are actually very important. But here's the cool thing about organic chemistry, why I love it so much. It literally is just the reaction of carbon with carbon, or carbon with nitrogen, or carbon with oxygen. There you go. That's it. But here's the cool thing. There's a lot of possibilities here. There's a lot of possibilities here. Okay? So we're going to build on this. And that's why in our lectures, I will make those some level of biological or medicinal background, because I want you to see the practical side of organic chemistry. How is it that fentanyl is made? Well, it's made right now in China. Most of it's made in China and it's being imported. How is it made? Well, this is an amide bond. It likes to break. Oh, so I could probably make that molecule there. Oh, this is an easy one to put on, so I probably could do that. Oh, that's a really easy group to put on, so that's probably how it's made. So I buy this, I buy this, I buy this, and I buy this, and I go to the lab and I synthesize it. Okay? So what we're going to learn in here is what we call retrosynthesis. How do I look at a very complex molecule, tear it apart, and build it back up? All right? Now, synthesis is the heart and soul of organic chemistry. It is the one thing that is the one main reason why organic chemistry is still the benchmark course for professional schools like vet, dental, medical, graduate. Because you can't memorize your way through organic chemistry. If you try, you're going to get frustrated. You have to understand what's going on with these little mini magnets, and that's the way I teach this course. I teach this through electronegativity. Remember that word? Back in GChem days, electronegativity. 4.0, remember this? How many times did I do that on the board? 4.0, 3.5, 3.5, 3.0, 3.0, 2.5, 2.0, 2.1, or 2.0, 1.5, 1.0, right? I go over and over, because that's why I know right here that this is a polar bond. This is a 2.5, and this is a 3.0. That means these electrons are heading in that direction. That means this is a positive. That means if I'm a big, mean nucleophile, I'm going to go right there. Okay, so that's why it is. The bulk of the chemistry in this course deals with what we call the carbonyl group. So with that, you see, what are the possibilities? Well, if I take a carbonyl and I put a hydrogen on it, well, that's a functional. It's called an aldehyde. If I put a carbon with another carbon, that's called a ketone. If I put a carbonyl with an OH, that's a carboxylic acid. If I put a carbonyl with an O carbon, or OR, that's an ester. If I put a carbonyl with a nitrogen, that's an amide. If I put a carbonyl with an alkyl halide, or a halide, that's an acid halide. Oh my word. And that's just 1, 2, 3, 4, 5, 6 functional groups that we have to learn how they're made and what they make. How to name them, what their physical properties are. See how exciting this is? We have a lot of ground to cover. And so with that, I think it's more helpful to say, oh, there's the amide functional group, and it sits right there on a practical molecule called fentanyl. Okay? So we're going to explore these functional groups, and we're going to do it pretty systematically. We're going to throw in a couple random chapters in here called organometallics and radical chemistry. But again, I'll do my best to make this relevant to what you'll see, hopefully, in the real world. We'll have an occasional quiz, not a lot of quizzes in here. I might do a couple quizzes on a Monday or sometime after a long weekend, just to make sure we're staying up and staying sharp. I'll let you know ahead of time. I don't surprise them on you. I'm sure you're all happy with the Achieve homework system. So I do it differently than Dr. Nogales. I'll explain that, just slightly different. It's basically similar to what I do at GChem. There'll be 4 exams basically, and then of course, final exam. So if you look at the topics that we're going to cover on the back, you can see that we're following a pretty standard course schedule. In this course, we're going to cover 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 chapters. So we do have some work to do. Some of these chapters I'm going to pare down. I love your textbook. Sorrel is probably my favorite textbook, and I've been teaching organic chemistry for over 30 years now. I've used a lot of textbook, and I think Sorrel does the best job of really the balance between chemistry majors and what you're going to need for graduate or for professional exams like the MCAT and the dental. So I try to find a good balance on that. Some of these chapters bog down though. All right, he gives a lot of information. So oftentimes I'll say, don't worry about this section of the book. All right, don't worry about 10.4 or whatever. Okay, because there's a lot of information in that textbook. And it's going to be overwhelming as it is, even if I don't throw some of this stuff out. So it might seem like we're going through a lot of chapters, but even like chapter 16, the organometallic chapter 15, I think we only have 2 lectures on it. And I pare that one way down in the Achieve homework. Okay? So that's our course semester. It's a really fun course. I really enjoy teaching the perspective, again, through the lens of this little tiny box called carbon. It's a pretty amazing molecule or atom in what it can build and some of the cool things that we can do with it. Okay, so I would love interaction. I would love for you to say, hey, time out, question, can you go back over that, or hey, can you clarify that? If it doesn't make sense, please ask, because I will try to teach it at a pace. Like I said, it'll be all this. It'll be chalk on the board with 3 different pens. Okay? So I really want us to get a grasp of this thing called organic chemistry. There's 4 main areas of organic chemistry, so this semester is going to utilize all 4 of them. First and foremost, there's going to be the functional group interconversions, okay? So you need to know, how do I go from a nitrile to a carboxylic acid? Maybe those 2 functional groups are foreign to you right now, they won't be after this. So a functional group transformation. Secondly, and probably the most difficult, by the way, functional group, well, I'll just leave it. Functional group transformation. Then we're going to move into some level of mechanism. Okay, how do these reactions actually go? How did I know that fentanyl is broken right here? Okay, if I'm an acid or a base, I know I'm going to attack here. Okay, especially if I'm a base, I'm going to attack there. How do I know that? Well, we're going to learn that. Okay, so mechanistic organic chemistry. All right, so we're going to deal with functional transformation, mechanistic organic chemistry. Thirdly, we're going to deal with spectroscopy. One of my absolute favorite classes to teach on this campus is structural elucidation. It's probably one of the most important courses for anyone going, especially to med school, because it teaches you how to assimilate data into an outcome. There's no other class that teaches that. How do you bring together the data from an IR, the data from an NMR, the data from a carbon NMR, the data from a mass spec, and synthesize it into a structure? It's exactly what my wife does all day long. Fever, rash, sleepy. Oh, IR, NMR, mass spec. How do you bring those together to propose an outcome? What other class teaches you that? It's a very, all chemistry majors get to take that. I had, this last time I taught, I actually had like 5 biology majors, which was awesome because they were pre-med. They just wanted to learn how that process works. So we will bring spectroscopy into this. In fact, next Tuesday, all we're going to do is spectroscopy. Okay, the whole lab is a structural elucidation experiment. I'm going to show you how to elucidate, and then guess what you get to do? You get to elucidate. Because in medicine, it's see one, do one, teach one. That's medicine. That's medical school. That's what my wife did constantly. Saw one, she got to do one, and she turned around and taught it to her lab partner. Okay? And you're going to do the exact same thing in elucidation, so that when we're taking NMRs throughout the semester, it's more than just N+1. Okay? Because I really want you to understand the aspects of that. And then the overall is going to be the physical properties of the organic molecules. Okay? What is the physical property of fentanyl? Fentanyl is not given like this. This is what we call the free base form. You don't give it in the free base form. They actually put a salt right here. If you'll remember back to Vesper, this nitrogen has a big long pair of electrons. So they actually bond that with a proton, which puts a positive here, so there's a chloride. So they make it a salt. Fentanyl without the salt is insoluble in the body. So they make it a salt. So what are the physical properties of these molecules? What are the physical properties of ethers? How do ethers differ from carboxylic acids? That gets us into things like pKa. I'll go back and explain pKa because that's a very important concept. It's probably the second most important concept next to electronegativity. Okay? So I'll have to probably reteach some of that, which is fine, I don't mind. They're now saying that we should probably go over something upwards of 12 times. It used to be 8 times to go over something to really let it sink in. And now we're probably up more closer to 12, between 12 and 15. I even heard as high as 18 times to go over something. So it's okay to go back over things, especially if you want me to go back over something. If you want me to go over the Kahn angle Prelog rules with RNS, you want me to do anything you want, I'll go back over because I enjoy this stuff. I actually just love this stuff. Okay? Questions? No questions. All right, that's not a good sign. Questions? Okay. All right, let's jump in with good old oxidation reduction. So, chapter, yes?
Just, you said that Achieve will be a little bit different than...
Oh, yeah, sorry. Yeah, I didn't get into that. Thank you. If you look at the course total, I actually have the homework worth quite a bit. And the reason for that is I know that some people don't test well, but they would rather spend the time in the trenches doing well. So I give you the opportunity. So I actually have homework worth quite a bit. I think it's worth 200 and the exams are worth 300. So I hope that, and I go through and I hand pick the problems. I don't just do the random thing and then you do most of them type of thing. So I hand pick the ones I really want to teach you with. And so the ones that are on are the ones that you need to do. Okay, and I think that's a little bit different than what Nogales does. Okay, cool, thanks for reminding me of that. Okay, oxidation reduction. Oxidation. Oxidation. What's that word sound like? Sounds like oxygen, doesn't it? It's probably because it is. Okay? This word stems from oxygen. So, where you start with oxidation reduction in all chemistry is oxidation means more oxygen. Okay? That's where you start. That's what the word means. If I put iron, back to GChem, if I put iron metal, fresh iron metal right out of the melting pot, you know, nice and shiny before you put the oil film on it, what does it do? It just goes bam, boom, right to iron oxide, right? A couple of forms of iron oxide, that's the main one, right? Takes those electrons. Oxygen, remember, is a very sinister. It wants electrons second most only to fluorine, right? So oxygen sees iron's 2 electrons and says, nope, they're mine. And so it goes over and grabs them, forming, again, 2 plus, 2 minus, okay? So it oxidized, it took electrons. So oxidation is more oxygen and or, whoops, and or, is that still recording good? And or less hydrogen. Okay. Now, back in general chemistry, those of you that had general chemistry, if you did, that's fine. Back in general chemistry, we talked about, I had a rule in Gen Chem, it was oxy loss. So you might remember that. Oxy loss. That's a good way to start, but that's a more broad understanding of oxidation. Oxy loss is oxidation is loss of electrons. That's exactly what happened to iron here. Iron had its 2 valence electrons. Oxygen said, nope, I got them. So it lost those electrons. So this has been oxidized. Iron has been oxidized. Oxygen has been reduced. So oxy loss was more of a general overview of oxidation. More specifically in organic chemistry, we're talking about, does carbon, because again, this is carbon chemistry. Does carbon have more oxygen and less hydrogen? Okay? Which means reduction is going to be the opposite. Less oxygen. And or more hydrogen. Now those are your rules. So the way I would memorize that and the way I would put that into the memory banks is starting with oxygen. Sounds like oxygen just means more oxygen. That's where it starts. So carbon has more oxygen, it's been oxidized. So when we take an alkane, let's take something as simple as methane. Okay? And I convert methane to methanol. What just happened to this carbon? Ooh, that's a dead one. What just happened to this carbon? It was oxidized, right? This carbon has 1, 2, 3, 4 hydrogens. This carbon has 1, 2, 3 hydrogens and an oxygen. So it gained an oxygen and it lost a hydrogen, did both. Okay? So this has undergone oxidation. Notice, I went from an alkane to an alcohol. Okay? If I take an alcohol and remove another hydrogen, what happened to this carbon. It was also oxidized, right? That carbon lost a hydrogen. It has the same number of oxygen, still has one oxygen, but it lost a hydrogen. Oh, less hydrogen is an oxidation step. So when I go from an alcohol, a primary alcohol, and lose a hydrogen, I go to an aldehyde. Huh, that's interesting. I've already talked about 3 functional groups: alkanes, alcohols, aldehydes. What did I say was one of the most fundamental things that we're going to learn in here? Number 1 was functional group transformation. Okay? Very important how these are interrelated. If I take this carbon and I go to a carboxylic acid, what just happened to this carbon? It's an oxidation step. And this is a carboxylic acid. Okay? That's another functional group. Pretty interesting. Now, if I take the carboxylic acid and I go here, what did I do?
Oh, you killed the carbon.
Killed the carbon. I oxidized it. And now, guess what? This is inorganic chemistry. There's only 2 molecules that don't count as organic molecules: carbon dioxide and carbon monoxide. They're inorganic molecules. That interesting? Here is something that I think is very profound, because again, and then this is just carbon dioxide. So this is just an inorganic molecule. Okay? Now, what I think is really special about this is there's a metaphysical reality to this. I love to delve into the metaphysics of science. This is one of the ahas to me. Because we have pretty good geochemistry that suggests that the primitive Earth, the carbon form of the primitive Earth was carbon dioxide. It's pretty good. Trapped in amber, trapped in crystals. They think the primitive Earth, a lot of the geochemists coming out of Stanford, where a lot of this is done, have a pretty good indication that primitive Earth was carbon dioxide. Now, that's a huge problem.
Because life can't come in.
Yeah, that's dead carbon. Does that make sense? Here's how do we now on Earth, terrestrial part of Earth, how do we alleviate this problem of dead carbon? You guys are biology majors. What uses carbon dioxide? Yeah, what do? They photosynthesize, okay? So here's why this is such a metaphysic concern, at least to me, and especially homochirality, which is another one. Plants are made out of alcohols. So when you look at cellulose, and we'll look at carbohydrates, when you look at the structure of cellulose, cellulose is a polymer of this form of glucose, okay? We can't digest it because we'll get into why this is, but for now, you have to just kind of trust me, I'll explain it when we get there. Rookie move, 4-5 on the card. Okay. So this is beta D glucose, and we will see this in this course. All right, we will talk about glucose, beta, alpha, D glucose, L glucose. We'll talk about galactose, fructose. We'll get into the disaccharides, polysaccharides. But here's what cellulose is. Cellulose takes another beta D glucose and puts it up here. It bonds with a special, the 6 and the 4. So this is 1, 2, 3, 4. This is a hemiacetal. Again, we'll get into that chemistry this semester. But here's what happens with this thing. And this is why this is important, because I want to challenge you not just in the chemistry realm, but in the life realm. Right? That's why we're at a university. Anybody know what university stands for, by the way? you're at a university. Isn't that weird? You ever broken that term down? Historically, the university, when we were talking Yale, Princeton, and Harvard, they came together and said, we are going to find unity in the diversity, in the plurality of the disciplines. How do we unify philosophy, chemistry, biology, business, religion? How do we unify those? And what was their answer? How do you unify chemistry with psychology, chemistry with business? How do you unify those? Ooh, that's a big question. That's a big metaphysic question. Well, if you look at their bylaws, the original in the mid-1700s, 1660, 1670, at the core, the only personality big enough to unify the diversity and the plurality was the person of Jesus. And that's why Princeton, Harvard, and Yale all founded on Jesus as the Logos, Jesus as the unifier of the plurality, and we called it the university. And then we kicked him out of the university. So now we have the plurality, and we're trying to figure out how do we unify chemistry with physics. It's not very easy anymore, because there's no personality big enough to unify. Isn't that interesting? So just that's where the word comes from. Now it's free. Now, with that, notice this. Here we have glucose. And you might be saying, why is he going through all this? And it's really important, because again, you guys are in that realm of the biology side of chemistry. So this just keeps going. And if I keep going with this, and I put another one down here, again, I put that down here, I'm not going to do it. And you can see that this quickly becomes this big, long polymer. All right? And this polymer is called cellulose. All right? Where have we heard of cellulose? What is cellulose?
Sugar.
It's sugar. It's made out of glucose, yeah. But where is cellulose?
Plants.
Plants. That's what plants are made of. We cannot break this. This is called a beta D glucose. And amylose and amylopectin, which is one we can break down to start, is reversed here. And this is anomeric center, which is cool chemistry. All right, so it's flipped. We can break that one down. We can't break this one down. Neither can goats, by the way. Neither can horses, by the way. But they have a bacteria in their stomach that can. So that's why they have multiple stomachs, because they chew that cud, and that bacteria breaks that down. But here's the deal. What's the plant made out of? Alcohols. Well, wait a minute. If primitive Earth was made out of dead carbon, where are the plants to break it down to form the plants? How do you reduce carbon dioxide? Because the laws of chemistry say, I can't. I have to have a living organism to do this process. That's very important. This isn't a small problem. The problem of dead or oxidized carbon in the primitive Earth, in the story, in the meta-story of origins, is very important. And as organic chemists, you should be aware of that problem. This isn't a small, trivial problem, because that carbon dioxide is reduced by a living plant. But the living plant is made out of living carbon. Once I have living carbon, then I can take that and go back and I can continue to, and that's exactly what we do. Okay, we just continue the chain. But if I only start with this, I have no chain. Okay, I have no cycle. And this is not a trivial problem, and if you actually do any research in this, you'll see that there's not a whole lot known about this. One of the leading theories, and I call them stories, is that there was a bunch of methane. Here's the cool thing. There was a bunch of methane that was trapped early on in the Earth's history. Here's the problem with that. The carbon footprint, carbon-14, carbon-13 ratio footprint of that what we call hydrocarbons down in the oil, we call it oil, matches living system. It was once a living system. Isn't that interesting? And I think that's important to just keep that in the back of your mind. And as you're questioning and building, that is not a trivial issue, because we're dealing with the heart and soul of organic chemistry being carbon, right? And we're going to be talking about oxidation reduction reactions in this chapter. So that's why this becomes, on a bigger perspective, to me, a very important question to ask and address. And be honest and open throughout that. We don't have a good answer for this. Okay? So other than, again, like I said, some people believe that the original Earth had this just in its formation, which is kind of weird, because if it has reduced, then why was primitive Earth made of this? So you just have to kind Scratch your head sometimes, go, huh? Isn't that kind of a little bit of a tautology there? Okay, so with that, let's do the other way. Let's take and let's reduce. So like I said, there's a line here. We're not going to cross that. So for us, we're not going to cross that line. And really, I'll put another line here. We're not going to do this reaction. Okay. Excuse me. We're really going to blanket ourselves between those two red lines. I just wanted to show you the whole picture of carbon because it's actually to me a fascinating process. So we're going to see that alcohols oxidize to aldehydes, which oxidize to carboxylic acids. Now, if I go the other way around, that's a good one. If I go the other way around, oh, you agree? Hey, photosynthesis might go. Serendipitous. So carboxylic acids reduce to aldehydes. Aldehydes reduce to primary alcohols. Okay? So this is really what we're going to study. We're going to see some reagents that do this for us. We're going to talk about some strong oxidizing and weak oxidizing. Pyridinium chlorochromate, pyridinium dichromate. We're going to see some strong oxidizers like chromic acid, potassium permanganate, and then we'll get into some reduction later in the chapter of, again, more of the specifics. Okay? But before we do that, let's go on with, continue the whole oxidation reduction thing of carbon. So carbon has a couple other forms of oxidation. One of them is if I go from an alkane if I go from an alkane to an alkene, what did I do? What happened to those carbons? Did they lose or did they gain hydrogen? Lost. They lost hydrogen. So what is that? It's an oxidation step, okay? So this is an oxidation. Huh. And if I go from an alkene to an alkyne, what happened to those carbons?
Oxidation.
They were oxidized. Okay? So this is an oxidation. So alkanes oxidize to alkenes, which oxidize to alkynes. Okay? Cool? Well, that's interesting. Because what's going to happen if I go the other way around? What do alkynes reduce to? Well, it looks like alkynes reduce to alkenes. Okay? And it looks like alkenes reduce to alkanes. Okay? So one of our very first reactions that we'll see in the oxidation realm is the reduction of an alkene and an alkyne, actually. They both reduce this way. So if I have an alkene and I want to reduce it to an alkane, how would I do that? Well, I would do that by a couple different reactions that we'll see. And again, we're going to start building. So this is a very important reaction. So if I take, bring my digital self over here. Okay, fine. So if I bring an alkene, okay, so if I take an alkene in the presence of hydrogen gas over palladium or platinum or nickel or ruthenium, one of those metals, they have to be the actual active metal, it goes to the alkane. Okay? All right? So, what's happening here? Well, here's what's happening. What believed, it's kind of one of those quasi, is that really what's happening?
the catalyst of the nickel, or the, and I'll tell you the difference between